Now, we've seen that atoms will emit only certain wavelengths of light. If you've got a hydrogen atom, it will only emit a red wavelength, a turquoise wavelength, a blue wavelength, and a dim violet wavelength in the visible range. Why? What happens to all the other colors? Why doesn't it emit all colors? Why doesn't it emit white light like an incandescent bulb filament will do? Well, the answer must be if it's only emitting certain discrete wavelengths, it can only spit out photons with certain energies. And why would it only be able to spit out photons of certain energies? Because maybe it's only allowed to take on certain energy states. When it moves from an allowed state to a lower state, it will spit out a photon that has an energy equal to the difference between those two states. Now that's pretty abstract. So let's look at an analogy that will maybe make it clearer. Suppose you've got a tortoise here, and the tortoise is stuck in a zoo enclosure that looks like a ramp. Now the tortoise is allowed to roam anywhere inside the enclosure here. Now you can tell what the energy of the tortoise is, the potential energy of the tortoise is at any given point. If you take the weight of the tortoise times the height of the tortoise above the bottom, you have its potential energy. So if the tortoise can roam anywhere in here, the tortoise can take on any potential energy allowed within the enclosure. Here it would have a high potential energy, here it would have a low, and it can take on an infinite number, really, of potential energies between those 2 points. Now, if you had an atom like that, the atom could take on any energy. And the photons that it emitted could have any energy. So you would see a continuous spectrum, a continuous rainbow. The one color would smoothly blend into another if this was the situation with an atom. But it's not. You only see certain discrete photon energies being emitted. Now, it must be more like this second tortoise in an enclosure that looks like this. Here the tortoise has different flat levels, and there's a steep drop between them. The tortoise is only going to be stable when it can sit flat. And if you tried to put it halfway between these two levels, it would fall to the next lower level. There simply is not a stable place for it to sit between these two levels. So you will see that the tortoise can only take on 3 energies in this enclosure: a high energy, a medium energy, and a low energy. What happens if this tortoise goes to the next lower level? Well, it's going to lose potential energy. The amount that it loses is going to be the energy it has at the top level minus the energy it has at the bottom level. And if this were an atom, and it went from this level to this level, it would spit out a photon that had an energy that was equal to the difference in energies between these two levels. So if you take the high energy minus the low energy, that's going to give you the photon energy. And you can see if the atom was trapped in an enclosure like this, there are really only going to be 2 lines. There'll be a line from going from here to here, and there'll be a line from going from here to here. I suppose you could have a third line if you went from here down to here. So every transition, every movement between stable energy levels is going to give you 1 line on the spectrum. And this is how we explain a line spectrum. And this is the significance of a line spectrum. The existence of line spectra tell us that the energies of atoms are quantized. Now, it turns out that the energy level diagram for a hydrogen atom looks like this. This diagram is only showing you the first 6 allowed levels. There's a lower level, a ground state they call it, and then there are excited states. The hydrogen atom is naturally found at this energy down here. And if you kick some energy into it, you have to kick exactly enough to take it up to this first excited state. So all of these states they'll call excited states because they have more energy than the ground state. Now what if you added this much energy to the hydrogen atom? It wouldn't absorb it. It wouldn't take you anywhere. If you had a photon with an energy that took you from here to here, it would not be absorbed by the hydrogen atom. It would just go right by, and the hydrogen atom wouldn't take it. But if you gave the hydrogen atom a photon that had an energy exactly enough to take it from the ground state to the first excited state, you would have promoted the hydrogen atom up to that excited state, and it would absorb that photon. If you shot another photon in, you might be able to take it from this state to this state if the size of the photon was right. Guess what? If you have a red photon, if you have a photon energy that will give you a wavelength of 656 nanometers, it will take you from this state to the next state up. And in fact, the red line on the hydrogen spectrum is this transition. It goes from here to here. And the difference between those two energy states is the photon for red light, the 656 nanometer red line. What if you want to go from this state, the first excited state, up to this state, the fourth state up? That photon energy, the difference between this level and this level, corresponds to that turquoise line on the line spectrum. So every line that you're seeing on the line spectrum is an allowed jump between two energy levels on this diagram. Now, not all jumps are allowed. So you can see that there's a lot of possible jumps that you could take here, but not all of them are allowed, and not all of them are going to show up in the visible range. This first jump that I talked about, from the ground state to the first excited state, if you calculate the photon energy there, it gives you a wavelength that's in the ultraviolet region of the spectrum. So there is a big, strong ultraviolet line in the hydrogen spectrum here, but you can't see it because it's in the ultraviolet. Now, how do we calculate these ground state, the ground state and the first excited state? How do we calculate the energies so that we can see what the energy level differences are? And so what the photon energies are going to be. Well, there's a simple model. It's called the Bohr model. We'll talk about that now. All right, here is the Bohr model, which will allow us to calculate the energies of the different levels that we've got in the hydrogen atom. Now, here's a little hydrogen spectrum that's inset here. And here in the Bohr atom, the difference between it and the Rutherford atom is that only certain orbits are allowed and no others. So the first orbit is this inner dotted line, this inner little circle, and that's the ground state, and the first excited state is here. There are no levels that are between the ground state and the first excited state. There are no orbits that the electron can take on. If it's going to go from level 1 to level 2, it's just going to suddenly snap into level 2. Now, if you look at the energies of these different orbits, they correspond to the lines in the line spectrum. Here, if you have you're in level 3, you have a certain amount of energy, and you snap down to level 2, the difference in energies between level 3 and level 2 gives you a photon energy that is exactly equal to the photon energy that you would calculate for the 656 nanometer line. So that explains the red line. It's a snap of the electron from level 3 to level 2. Now, if you want to explain the turquoise line, it's just a different pair of levels. You're going from level 4 and snapping down to level 2. The difference between those two levels gives you the photon energy that you would get if you had this 486 nanometer line and turn that into a photon energy the way we did in the last lesson. That's exactly equal to the energy level difference between level 4 and level 2. So the photon energy is the energy level difference. Each line in the line spectrum is a jump between two energy levels. And you can explain the lines in the line spectra that way, for hydrogen anyway. Now, how do we get some numbers for these? Because I'm saying, you know, if you calculate the difference in energy between level 3 and level 2, that's the photon energy you get with the red line. Well, how do I know what these energies are? Well, using some fairly basic physics, Bohr calculated an equation for the energy levels. Let's call the energy of a particular level E, and let's put a subscript N on it. Now this N is kind of a label for the energy level. N equals 1 is the label for the first level, N equals 2 is the label for the second level, and so on. That has a name, and we're going to see it again and again in, on Friday. Well, in the next lesson, I should say. And it's called the principal quantum number. And I can calculate the energy of level N as minus, there's a minus sign here. Why? Well, energy 0 would be a proton with an infinite distance between the nucleus and the electron. So you've essentially pulled the electron completely off of the atom. You'll call that energy 0. Now, as you bring the electron in, here's the nucleus. If you bring the electron in closer, that is going to lower the energy. So all of the energies of the hydrogen atom are going to be negative numbers. That's why the minus sign there. And then there's a constant. It's called the Rydberg constant. Your book uses a different symbol for it. It's kind of a script R. I'm going to use the symbol that everybody in real life uses. And then it's got an H for a subscript, minus RH. This is a constant. It happens to have a value of 2.18 times 10 to the minus 18. If you look at the basic physics of this atom right here, you can calculate what minus RH is from first principles. Ab initio, we said back in module 1. And you can use Planck's constant, the speed of light, the mass of the electron, some other things go into calculating what this constant actually is. But it's 2.18 times 10 to the minus 18 joules divided by n squared. So this is the Bohr model. It lets us calculate the energies of these different levels. If I want to calculate the energy of level 1, it's going to be minus 2.18 times 10 to the minus 18 divided by 1 squared. So essentially, the energy of level 1 is minus 2.18 times 10 to the minus 18 joules. Okay? Now, if you take the energy of the ground state minus the energy it would have if the electron was completely ripped off, which is 0, that would give you the ionization energy of the hydrogen atom. It would give you the amount of energy you need to pump into the hydrogen atom to completely tear the electron off. And that's why the ground state is 2.18 minus 2.18 times 10 to the minus 18 joules. That happens to be exactly the amount of energy it takes to pull an electron off of the hydrogen atom. It is the ionization energy of the hydrogen atom. We'll play with this a little bit in the next slide. If you've got the atom in this state, the ground state, the Bohr model predicts that the energy is going to be minus the Rydberg constant minus 2.18 times 10 to the minus 18 divided by 1 squared, because this is level 1. Now we can calculate the energy of this state from the Bohr model, it's going to be, this is level 1, this is level 2, so the level numbers start with 1 and they just go up. And if it's level 2, it's the energy of this is going to be minus the Rydberg constant, 2.18 times 10 to the minus 18, divided by 2 squared, divided by 4. And if you put that into your calculator, you'll see here is the energy of the first excited state. If you take the difference between this energy and this energy, that gives you the energy of a photon that is dropping from level 2 to level 1. And the question below this video asks you that. What's the energy of that photon? And all you've got to do is take the difference between those numbers to get it. Now, you can take that photon energy and use what we learned in lesson 3.1. And you can turn the photon energy into a frequency and then turn it into a wavelength. And that's what the question is asking you to do. So you might want to look at the last question on the previous lesson, because in that question, we're taking a wavelength, a frequency, and a photon energy, and we're calculating one from the other. And you're doing the same thing in this question. Now, in the Bohr model, notice that I'm showing more energy levels here. The energy levels get closer and closer together the higher and higher you go. The top level is at 0. So if you take the difference between the ground state and the top level, which is where the electron has been completely pulled off, that gives you the ionization energy for the hydrogen atom. Now, I've said that once before, but that's kind of important, okay?